All right, welcome back. I think we're ready to start the 13th Spotlight session. So the first paper is on a polynomial time solution for robust registration with extreme outlier rates. And the talk will be given by Heng Yang from MIT.
Hello, everyone. I'm Heng Yan from MIT. It's my pleasure today to present our RSS paper, Polynomial Time Solution for Robust Registration with Extreme Outlier Rates. This is joint work with my advisor, Luca Colone. So point cloud registration is a fundamental problem that has many applications in robotics. For example, it can be used for object detection and localization, which is an important part for autonomous driving, smart manufacturing, and domestic robotics. Besides this, registration is also crucial for localization, navigation, and mapping. So in order to register two point clouds, we can first extract feature points and then match feature points to establish correspondences. Then the registration problem can be formulated as a least squares optimization, where we try to find the best scale, translation, and rotation so that the sum of the square distances between 2 point clouds is minimized. When all the correspondences are correct, the registration can be easily done using a closed form solution by Horn. However, in practice, many of the feature correspondences are actually wrong. Therefore, it is popular to apply RANSAC and M estimation to deal with outliers. But as shown by these two videos, both RANSAC and M estimation can easily get stuck in local minima in the regime of high noise and high outlier ratios. A recent method called guaranteed outlier removal can tolerate above 95% outlier rates, but this method is suboptimal and also runs in exponential time. Our method, teaser, uses a truncated least squares cost function so that the outliers have no effect on the optimization. Solving this optimization, however, is extremely hard. Therefore, our key contribution is to decouple the estimation of scale, rotation, and translation, and to develop polynomial time algorithms for each problem. In order to decouple the estimation, we propose to build invariant measurements. The first insight is the relative distance between any 2 points is invariant on the translation and rotation, and only depend on the scale. The second insight is the relative positions are actually invariant to translation. Using invariant measurements, our first step is to estimate the scale using adaptive voting. So the intuition behind adaptive voting is very much like plotting a histogram. We can break the range of measurement value into many bins, and then we can count the number of measurements inside each bin. The bin that has the highest voting will contain the estimated scale. Luckily, adaptive voting is guaranteed to return the optimal solution. Our second step is to estimate the rotation using a semi-definite relaxation. So the magic behind STP relaxation is to lift the decision variables into a higher dimension space so that the original non-convex problem becomes convex, in which case we can guarantee to find the global minimum. Empirically, our STP relaxation is exact or tight, even with extreme outlier rates. Our last step is to estimate the translation using component-wise adaptive voting. In this step, we treat the X, Y, Z components of translation separately and apply adaptive voting 3 times to get the optimal estimation in each direction. We tested teaser against several state-of-the-art methods in simulation. This plot here shows the rotation error in degrees with increasing outlier rates from 95% all the way up to 99%. As we can see, both RANSAC and M estimation fail very badly in this situation. Our method, teaser, which is shown in blue, is robust against 99% outlier rates and returns the most accurate solutions. The second best approach, GORE, although being similarly robust, is actually an exponential time algorithm based on branch and bound. We also tested teaser on real-world RGBD datasets for object post estimation, as can be seen by these two examples. Even when there are more than 95% outliers in the feature correspondences, teaser is able to find the inliers and estimate the post with very high accuracy. And with that, I want to thank you for your attention and invite you to come to our poster for more discussion.
Thank you. So the second talk will be on a modular optimization framework for localization and mapping, and will be given by Jose Blanco Claraco.
So, hi everyone. I'm presenting a localization and mapping framework. And the main motivation behind this work is basically a frustration trying to put together different kinds of front ends for different kinds of sensors. Nowadays, it is really difficult to put several of these works together. So Ideally, a SLAM framework should be something flexible that allows you to switch between 2D or 3D mapping, mixing different kinds of sensors. And our framework tries to do that, okay? By changing a few lines in a configuration file, you should be able to switch between reading from an offline dataset or reading from a real-time sensor like a Velodyne LiDAR. So let me introduce an overview to the architecture of the system. We start with this like a system loader, which is in charge of rising up the rest of the modules in the system. We have blocks that works as sensor inputs. They may read from a real sensor of a data set. Then we have that information fed into the different front end for different kinds of sensors, like vision or LiDAR. And then we have a unified interface to the SLAM backend, which inside has the graph solver. And this this SLAM backend is talking to the world model. The world model actually is basically a graph where the nodes may be some stuff like keyframes, or they may be the relative position for the calibration of cameras, for example. And we also have relationships between the different entities. Basically, you can think of that like factors in a factor graph. In this slide, I show how to a real-world trajectory from a robot of a camera is mapped into some structure in the world model on the top, and then the corresponding factor graph on the bottom. In this particular case, using kinematic constraints for a constant velocity model. And by switching the kind of map, you can get a totally different representation. For example, here we have a relative coordinates using sub mapping. And the front end knows nothing about this decision. So everything lies inside the SLAM backend. So let me present now the LiDAR pipeline that we are offering here in this paper. Basically, we have a pipeline with a filter, then we have a data structure for multi-feature, multi-layers point clouds, and then a set of different ICP algorithms. Every single part of this pipeline can be extended by the user. So you can focus on doing research on a new ICP algorithm or a new detector, and then benchmark the result against the alternative configurations. In particular, the ICP algorithm that we have introduced here is a modification of the Horn solution that is able to handle point-to-point and lines and planes correspondences. We can check out that supplementary paper for that. Here you are watching at a live demonstration of the system, which is running a 3D graph SLAM problem using the LiDAR sensor from the Kitty dataset. On the left, you have the raw input to the system. On the right, the map that is being built online, including loop closures and everything. It runs like twice real time, but there is room for improvement in every single part of the framework right now. And by changing one parameter of the system, you include, for example, in this case, the velocity of the vehicle into the system. And is these small green arrows that are being displayed there? It is the velocity that is being estimated online by the backend. So basically, we already have a system that is usable, but there is a huge amount of future extension to this framework. And I invite you all to give it a try. It is open source at GitHub. So thank you.
So the third presentation will be on high throughput computation of Shannon mutual information on chip, and will be given by Peter Lee from MIT.
Good morning, everyone. My name is Peter Lee. I'm a graduate student at MIT. Today, I'm very excited to present our hardware for high throughput computation of Shannon's information on chip. This work is done in collaboration with Zhendong Zhang, Satosh Karaman, and Vivian C. The goal for autonomous exploration is for the robot to map the environment in the shortest amount of time. Many existing algorithms use Shannon's mutual information, which allows the robot to decide the next best location on the map to scan the unknown environment. An exploration experiment is shown on the right, where the robot travels to the location with the highest mutual information on the map to make the scan. Thus, computing mutual information at more locations allows for more optimal selection for such scan location. From now on, I would like to use MI to refer to Shannon mutual information. Computing mutual information at any given location on the map is extremely parallel in nature. because MI for different beams can be computed with multiple cores in parallel on the hardware. Since each core requires one memory read from the occupancy grid map every cycle to remain active, the throughput of all the entire system requires each core to have its own independent memory read port so it can independently access the map for MI computation. However, standard energy efficient memory only contains a maximum of 2 read ports, which severely limits the number of cores that can be active at any given time. Thus, we decide to partition the storage of the map into multiple memory banks to provide more read ports for the cores to use and increase the memory bandwidth as a result. To find the optimal banking pattern, we know that all the cores access the same row or the same column of the occupancy grid map every cycle, as shown on the left figure. Since each bank only contains 2 ports, our strategy is to let the cores access different banks every cycle to avoid multiple cores fighting over the same ports from the same bank. Thus, by diagonally partitioning the storage of the occupancy grid map, shown on the right, we're able to maximize the data delivered bandwidth to all the cores because no more than 2 cells from the same bank occur in each row or column of the map. For our final design, we diagonally partition the storage of the entire map into 16 dual-port memory banks, which provides enough bandwidth for 16 cores. We tested our entire system on a Xilinx FPGA, and we plotted the system throughput versus number of cores. If the memory has infinite number of read ports, we expect the system throughput to increase linearly with number of cores, which is shown with a dotted black line. On the other hand, if we were to store the entire map in a single dual-port memory banks, our system throughput will be heavily memory bandwidth limited, which is shown with a blue line. By using our diagonal memory banking architecture, our throughput falls within 94% of the theoretical limit, which is shown with a purple line. In all, our entire hardware system computes MI for the entire map at 2 Hz, which is more than 100x faster than a similar computation on Intel Xeon CPU, while only consumes 2 watts, which is 10x less than the same CPU. In summary, we found that having a parallel algorithm is not a sufficient condition for high throughput computation on specialized hardware. In fact, we argue that the hardware is often limited by its memory architecture and the data delivery method to all the cores. By using a diagonal memory banking architecture, our hardware computes MI for the entire map in near real time with very low power. Please stay tuned for our upcoming journal paper and see you at our poster session. Thank you.
The next presentation will be on approximate Bayesian inference in the spatial environments and will be given by Atanas Mirchev from Volkswagen.
Hi all, my name is Atanas, and today I want to talk a little bit about moving agents and the environments they operate in. And this is some work we did with Baresh and Tiosin in the Machine Learning Research Lab in Munich. The motivation for this is basically bridging the gap between modern advances in variational inference for deep space-based models, such as the one you're going to see on your right over there, and tasks that need to be performed in spatial environments. So to this end, we propose our deep variational Bayes filter with a latent map component, which you see a probabilistic graphical model for on the right. And this model has a learnable transition and a learnable emission model, which are parameterized through neural networks. Now we're hopeful that with this model we can tackle tasks such as system identification, SLAM, navigation, and autonomous exploration in a unified framework. And just for your convenience, Z's are going to represent agent poses, U's are controls, X's are observations, and M is our map. And now, in the rest of this talk, I'm just going to illustrate how we approach the different spatial tasks. So we start out with simultaneous localization and mapping. And in our deep probabilistic model, this comes down to obtaining posteriors over the agent poses and over the map variable, which are done with black box variational inference with a traditional elbow that's very typical for generative models. You can see the model performing on the right in a Wisdom simulator where the observations are images and localization is successful. We see that the localization error does not really compound over time, which is an indicator that SLAM is working. On the bottom right, you can see some emissions from the learned map as the training process progresses. And the model is fully probabilistic, so we retain all uncertainty about every single component. Now, one major thing that I want to illustrate here is that we can switch modalities by just changing the emission model. So the system is modular, which comes from the fact that it's a state space model, so you can easily exchange the learned components for something else to model different modalities. The next task that we consider is navigation, and for this we apply our model to a new environment that hasn't been seen before, learn a map for it, and then use the model as a simulator for the world to completely do planning in it. And here we illustrate that with a star search, for example, we can still achieve a 100% success rate of navigation from one post to the other. And of course, any ordered reinforcement learning or optimal controls policies can be used to construct plans in our model that just acts as a substitute for the real world because it's a generative model. The final task that I want to illustrate now is exploration, and that's how to explore a new unseen environment efficiently. And we have a fully probabilistic model, which means that we can utilize information gain and devise the whole scheme with information theory to maximize the information gained about the random variable of the map. So this comes down to just doing an optimal control task for maximizing the mutual information between future predicted observations and the map variable. And as you can see, our model significantly outperforms a deterministic baseline, which is an LSTM network, which does not have the probabilistic assumptions and structural inductive biases that we impose on our model. So throughout all of this, we had to face two major challenges. The first one was that we need to model very long trajectories, and standard backpropagation through time for learning does not really scale. So we had to introduce a new approximate particle scheme for our post-posterior, which makes it possible to use GPUs and do mini-batching. The second major challenge is that of perceptual aliasing, which is very, very typical for spatial environments. It leads to multimodal posteriors over the poses, and this we tackle with a particle filtering variational family for our approximate posterior. So thanks for your attention. You know where to find us. If you have many questions, please feel to do so. Thanks.
Thank you. So the final presentation will be on systematic handling of heterogeneous geometric primitives in GraphSlam optimization. And the talk will be given by Irvin Aloise.
Okay, hello everyone. I'm Irvin Aloise, and I'm going to present a work that we developed in our lab at Sapienza University of Rome. That is called Systematic Handling of Heterogeneous Geometric Primitives in GraphSlam Optimization. So a bit of background, we are in GraphSlam, and we want to perform global optimization, so we want to optimize both the trajectory of the robot and the position of landmarks. So we have a different kind of landmarks that can be used in this context, from lower dimensional geometric primitives like points to other primitives like lines, planes, and so on. The use of higher dimensional primitives actually brings several benefits to the system because it better represents the environment and also, in general, enhances the convergence of the system. However, dealing with this object in an ad hoc manner may result in a system that is less compact. So what we propose here is actually novel formulation that is able to represent these primitives like points, lines, and planes as a unique object that is called matchable. So a matchable is actually a degenerate quadric, and so we represent each of these objects, for example, a point as a degenerate sphere, a line as a degenerate cylinder, and a plane as two planes with null distance. So using this formulation in our problem, we are able to actually combine the benefits of having higher dimensional primitives, as I said before, so the better description of the environment and the potential reduction of the memory footprint of the map, together with a compact implementation, so an easy system, easy to implement system, and most importantly, the ability to generate heterogeneous observation of the landmark. For example, if we have a landmark that is a plane, we can actually sense it, so observe it as a line or as a point, and so on for also the other primitives. So in order to validate our claims, we performed several experiments. The first one actually are made on synthetic datasets and should appear soon. In this sense, we actually, in this context, we compared the evolution of the chi-square of the optimization process using our formulation that in those graphs is in blue with the point-only approaches that are in green. And we varied both the noise conditions, so the noise figure applied to the measurements, and also the initial guesses. So as we can see from those plots, actually our formulation, as expected, has a better robustness to noise with respect to point-only approaches. Finally, we also embedded this formulation in a full SLAM pipeline, where we process actually RGBD data to construct a graph. And we then perform a global optimization, so both on the poses, on the trajectory and the landmark, and we evaluate the absolute trajectory root mean square error. As we can see from this table, despite the simplicity of the front end that has a great impact, actually, we are able to achieve results that are comparable with other state-of-the-art RGBD systems. So that was all. And if you're interested and you want to know more about it, just have a look at the paper downstairs. Okay, thank you.
Thank you. So I would ask all the speakers to join me on the podium. Thank you. So any questions for the speakers?
Hello, I had a question for the first talk. Thanks for the interesting ideas. I guess the assumption is that the outliers are kind of randomly. So do you think that can be expanded to several identical parts in the same cloud?
What's the last sentence you said?
Do you think that can be expanded to the case where you have several of the objects in your point cloud?
Oh, yes, yeah. So, right now the assumption on the outlier is that it's randomly generated. But we do have another paper that's on arXiv that's, actually not on arXiv yet, but will show that when you have multiple objects, this SCP relaxation will give you a rank 2 solution, and then which correspond to the 2 objects in the scene. So that's quite interesting.
Thanks.
So this question is for the third speaker. Have you done any baseline tests with GPUs?
That's a great question. Currently, we have not for this paper. But let me just remind you that the purpose of the talk is to remind everyone that the throughput in this case is not limited by compute. I know that GPU has a lot of compute in it, but the throughput for this application is limited by memory bandwidth. So if we were to implement on this GPU and the map is stored in like a single memory, you would likely run into the same issue, which limits the compute.
So from my understanding, some GPUs have multiple memory hierarchies, and they tend to also have very high memory bandwidth. So have you compared, like, for example, a GPU that has gigabytes per second memory bandwidth with the custom solution you propose?
Okay. That's a great question. So not at the moment. So if the GPU has multiple memories, let's say if you store like the banking pattern in that way into the memory, you might get a better performance, but the power is not really comparable in this case. So in this case, on the FPGA is 2 watt. If we do ASIC, preliminary simulation will be 10x even less than that. So on the GPU, it would be more than 100 watt, which is really not suitable for our application on miniature drones.
Other questions?
Question for Jose. So first of all, the framework is super useful, so I'm really glad you're doing this. For direct methods for SLAM, like where you use photometric error, the distinction between front end and back end is a little bit thinner in the sense that you alternate like pose optimization and mapping. Do you envision that the framework can capture that eventually, and do you plan to do so?
Thanks. So thanks for the question. Actually, that distinction should lie inside the barrier of the front-end module. So inside the front end, you may use whatever, you may even build like a local map and do whatever the technique, direct visual odometry, whatever, inside the front end. And then you have to tell the result of the local map optimization to the SLAM backend. So it can be merge with other sensors. But I think that it should be feasible to integrate that, yes.
Thanks.
Any additional questions? Well, let me ask a question to all the speakers. What do you think, and please try to summarize that quickly, is the key limitation of your work, and how do you plan to address it?
Okay, yeah, good question. So I think for us, right now the biggest challenging is how to speed up the whole process. And for that, I actually have two comments to provide. I think right now the bottleneck is on solving SDP fast. So I think this is ongoing research. Probably the audience already has a lot of experts on this. So we would hope to use some other specialized solvers to solve SDP as fast as we can. And then the second comment is that although the SDP is a bottleneck, but our whole framework is actually very useful. So we can replace some of the sub-problem solvers with some other solvers that's faster. But in that case, we would probably lose some theoretical guarantee in that sense. But for efficiency, this would be a trade-off.
Okay.
Yeah.
So for the case of this framework, probably one of the most difficult challenges ahead is trying to take some of the state-of-the-art algorithm and try to rewrite them in the language of this framework, so they can be split into the smallest possible part, and so people can start playing to optimize one of each of these step of the algorithms. So I would say that's the challenge.
I guess one, ASIC is typically very fast, but one major drawback is that once you have the design fixed, let's say on a chip, you cannot change it anymore. So let's say next week you have a better algorithm, you can't just suddenly change the chip. So that's definitely one of the drawbacks. But I think as for my design, I try to make the ASIC tunable as much as reconfigurable as much as possible. So you can change different parameters such as scan density. So you'll be although the design is fixed, you can use it for a variety of applications.
Thanks. So I guess the first point I would address as a weakness would be the weakness in terms of the pragmatic aspects of applying the framework to real data is that the computational load is pretty much high currently because of all the stochasticity in the model and also because of all the learned component. And we are actively working on this. And basically also that aligns with another point, which is there are difficulties in terms of designing the framework such that we keep it generic enough, such that we can learn as much as we can and extend to different modalities and so on. But also we should provide the right priors in there such that the system can be effective and can utilize as much knowledge as we have for the particular cases. So this is just work in progress. And
Okay, maybe the most tricky part of our implementation is actually not in the back end, but in the front end. So actually detect those primitives, and for example, also the data association could be an issue, because also if you have to perform cross constraints, that could be actually a little bit tricky. But in general, also maybe also the speed in which you can actually process data, but it's always on the front end.
Okay, I think we have very last question.
Yeah, question about the robust registration. If I understand it correctly, you estimate the scale by computing statistics about distances of points in the point clouds. Which assumptions are you doing about the overlap of the two scans that you have? So are you assuming to have serious overlap in the scans, or can you also deal with partial overlaps, because then the statistics may change?
So yeah, we don't assume like overlap, or what percentage of overlap exists in the 2-point clouds, right? But when you have partial overlapping, then when you detect the features, you will have a lot of outliers, and that's and then when you calculate the so-called the relative distance ratio, you will get a lot of scalars, and then you do the statistics. But this is combining the 2-point clouds, not for each point cloud. So the statistics is for the relative distances, and then you calculate the ratio. So it's not like we calculate the statistics for point cloud A and then calculate for point cloud B. It's combined, so that wouldn't depend on the overall matching.
All right, thank you. With that, I think we can wrap up this session. I would like to thank the speakers. Thank you.